Imagine handing a computer nothing but the rulebook to chess, walking away for a few hours, and coming back to find it has not only learned the game from scratch, but is now beating the strongest chess engine humanity has ever built. That is essentially what the AlphaZero paper demonstrates, and the implications go well beyond board games. To appreciate why this is striking, you have to understand how computer chess has worked for the past several decades. Programs like Stockfish, the reigning world champion engine at the time of this paper, are marvels of human engineering. They search tens of millions of positions per second using what's called alpha-beta search, which is essentially a brute force exploration of possible move sequences, pruned cleverly so the program doesn't waste time on lines that are obviously worse than something it has already considered. Crucially, when these engines reach the end of their search and need to judge whether a position is good or bad, they rely on an evaluation function that has been handcrafted over decades by grandmasters and programmers. It encodes ideas like the value of a bishop pair, pawn structure, king safety, control of the center. This is deep human knowledge poured into code. Shogi engines like Elmo work the same way. Powerful but bespoke to their domain, and useless if you handed them a different game. Then came AlphaGo and its successor AlphaGo Zero, which took a radically different approach for the game of Go. Instead of handcrafted evaluation, they used a deep neural network to look at a board position and output two things: a policy, which is a probability distribution over moves saying which look promising, and a value, which is a single number estimating who is winning. AlphaGo Zero learned all of this from scratch through self-play, with no human games as input. But Go is unusually friendly to neural networks. The board is spatially uniform. The rules have rotational and reflectional symmetries, and outcomes are simply win or loss. Chess and shogi are messier. Pawns move differently depending on where they are. Castling is asymmetric between kingside and queenside. Queens can fly across the board in a single move, creating long-range dependencies, and games can end in draws, which matters strategically. The contribution of AlphaZero is to show that the same general algorithm, with essentially no domain-specific tweaks, can master all three games. Here is how it works. There is one neural network that takes a board position as input and outputs both a vector of move probabilities and a scalar value estimating the expected game outcome from that position. To actually choose a move during play, AlphaZero does not just trust the network's policy output directly. Instead, it runs Monte Carlo Tree Search, which you can think of as a kind of guided imagination. Starting from the current position, it simulates playing forward, and at each step, it picks moves that balance three considerations: moves the network thinks are promising, moves whose simulated outcomes have looked good so far, and moves it has not explored much yet. After running many such simulations, it picks the move that was visited most often in the tree. The search uses the network as both a compass and a judge, and the search in turn produces better move recommendations than the raw network would on its own. Training is a beautiful feedback loop. AlphaZero plays games against itself using this search-guided procedure. When a game ends, the actual outcome, win, loss, or draw, is propagated back through every position in that game. The network is then updated through gradient descent on a loss function that does two things at once. It pushes the value prediction toward the actual game outcome using squared error, and it pushes the policy prediction toward the move distribution that the tree search actually used via cross-entropy. A small weight regularization term keeps the parameters from blowing up. The intuition is that the tree search is smarter than the raw network, so the network learns to imitate its own search, and the search in the next iteration is then guided by a smarter network. The two bootstrap each other upward. There are some subtle but important changes from AlphaGo Zero. Because draws matter in chess, AlphaZero predicts expected outcome rather than probability of winning. Because chess and shogi are not symmetric, AlphaZero does not augment training data with rotations or reflections. And rather than periodically checkpointing the best player and only generating new games from that frozen best version, AlphaZero just continuously updates a single network and always uses the latest parameters. Hyperparameters are not tuned per game, with the lone exception of exploration noise, which scales with the typical number of legal moves available. The results are stunning. Starting from random weights, AlphaZero surpassed Stockfish in chess after just 4 hours of training, surpassed Elmo in shogi after 2 hours, and surpassed an earlier version of AlphaGo after 8 hours. In head-to-head matches, AlphaZero did not lose a single game out of 100 against Stockfish and won decisively against Elmo and AlphaGo Zero. And it did this while searching dramatically fewer positions per second, about 80,000 in chess versus Stockfish's 70 million. That's nearly a 1,000-fold reduction in raw search throughput, compensated by the network's ability to focus attention on the variations that actually matter. This is closer to how a human grandmaster thinks, considering a handful of candidate moves deeply rather than exhaustively enumerating possibilities. The authors also showed that AlphaZero independently rediscovered most of the popular human chess openings during self-play and then often outgrew them, sometimes abandoning openings that humans favor. Now, the limitations deserve honest attention. AlphaZero required enormous compute, 5,000 first-generation TPUs to generate self-play games and another 64 to train the network. This is not something a researcher reproduces in a garage. The comparison to Stockfish has also been contested by the chess community, since Stockfish was run with a relatively small hash table and at time controls that may not have been optimal. The paper does not deeply explore whether the approach generalizes to imperfect information games like poker, or to environments without clean reward signals, or to problems where self-play is not a meaningful concept. And while the algorithm is general across these three games, it still assumes a turn-based, two-player, zero-sum, deterministic, fully observable setting. That's a narrow slice of the world. Still, the conceptual demonstration is profound. A single learning algorithm, given only the rules, can reach superhuman performance in domains that took humans centuries to master. Now let's walk through some questions you might have after hearing all of this. Why does the tree search produce better moves than the neural network alone if the search is guided by that same network? The key is that the search aggregates many look-aheads. Even if the network's snap judgment about a position is noisy, by simulating forward and seeing how things actually play out down the line, then averaging the value estimates at deeper positions, you get a more reliable signal than evaluating the root position directly. The search is essentially using the network many times to triangulate a better answer, and the policy targets the network trains on come from this improved signal. What is the role of self-play, and why doesn't the network just get stuck playing weak moves against itself forever? Self-play works because the search always finds improvements over the current policy. Even at random initialization, the tree search can stumble on outcomes that distinguish slightly better moves from slightly worse ones, and those tiny signals get baked into the network. Then, in the next generation of games, the network is marginally smarter, the search becomes marginally sharper, and the cycle compounds. It's a curriculum that automatically scales in difficulty because the opponent is always exactly at your level. Why did the authors drop the practice of only generating self-play games from a verified best player? In AlphaGo Zero, they would freeze a champion network, generate games from it, train a challenger, and only promote the challenger if it won 55% of evaluation matches. The reasoning was safety. Don't pollute training data with a regression. But this gating is conservative and slow. AlphaZero showed that just continuously updating one network works fine in practice. presumably because the gradient updates are small and individually low risk, and the system self-corrects from any temporary dip. Simpler and faster. So how do these ideas translate to large-scale recommendation systems? The most directly transferable lesson is the policy plus value architecture combined with a search procedure that improves on the raw network's output. In a ranker, you might train a model that predicts both a distribution over candidate items and a value estimate of long-term user satisfaction from a given user state, then use a lightweight search at serving time to roll out hypothetical sequences of recommendations and pick the one with the best projected value. This is essentially model-based reinforcement learning for sessions, and it directly addresses the chronic problem that point-wise ranking models optimize immediate clicks rather than downstream user trajectories. The self-play training loop also maps onto offline simulation. You can train a user response model and then let your ranker play against it, generating synthetic trajectories that improve the policy in regions where real logs are sparse. The harder lesson is about compute economics. AlphaZero's trade-off of fewer smarter evaluations versus brute force is appealing for retrieval and ranking, where latency budgets are tight and you cannot score a billion candidates per request. A learned policy that focuses search on the most promising slice of the catalog, combined with a value head that estimates long-term engagement rather than next click probability, is exactly the right shape of solution for production. The catch, of course, is that recommendation environments are partially observable, non-stationary, and feature delayed and noisy rewards, none of which apply to chess. But the architectural blueprint of network-guided search, trained by bootstrapping its own improvements, is one of the more underused ideas in industrial recommendation today.